Hello, humans. It is I who is live. Hopefully, I'm live. Let me just verify it once. Is Mo live? Yep, Mo is live. Great. This is great news. Just get the chats in here. The Chateaubriand. Your videos. Yep. And live. I am in fact live. What's this? Shut. Don't want to hear my voice. Wanna pop out chat? Yep. Let's go back. Hey, does views decrease? Like, can you like take away views? I don't know. Huh. So, still trying to create the transformer. That's what we'll be doing today as well. Trying to build the transformer. What's the problem with the initiation? So like fix that right now. I did not know you have to like actually mark it as none for this to work. I'm also very tired today for some reason. Should work for that. Then you go into your decoder. And yep, that should do it. That should fix encoder and decoders. Where's my encoder? Encoder also is fine. Decoder should also be fine. Yep. Let's run this. And with that, I believe initial set of errors have been resolved. After this, we'll be going into our coding. Yep, we'll be trying to resolve the other problems. I'm too lazy to do all of them. Today we'll try to do this one, this one, and this one, these three. And if after these three we are not tired, now if we get bored after doing these three, we'll like try to do we'll play games. Yeah. For now, waiting for this to run. By the time, let's look into something. Let's What should we look into? Any fun thing to watch? How to build a stream career. Who are you? Do I know you? I don't know you. Okay. Sorry, I started streaming. I don't know you, bro. I don't care. Who are you? Do not care. Je ne care pas. I mean, I do care about them, but I don't want to bother watching. I'm too lazy. Just want to code. So it's sitting code. Let's code stuff. So what have we been building till now? We have our model, which will take like a lot of time to run. I'm running on a very small data set. Obviously, the calculations won't be long. Let's see backtracking, how to do the backtracking for attention. So we go to a trusty back propagation for attention is all I need transformer. I was wondering, okay, if here also they don't say anything about transfer or the back propagation, I'm confused. And I know about RNet. Architecture traditional RNet. Good, I know how RNet works also. I don't know the backpropagation of RNN. If I just want to know the backpropagation of RNN, it won't take much brain cells for me. LSTM also fine. Attention plus CNN. I thought this attention does not need CNN. Okay. Not the most useful information. I know that that's a shit. This whole thing is proving to be just pissing me off. Waste. Just waste. Give me some information, some idea of how backprop works. That's why now. Yeah, let's see. Let's see. Okay, so what they're saying is you get the initial probabilities, you get the output, calculate the loss. After you calculate the loss, then you calculate the new weights by dl by the wq, wc, and wv. So that's the only thing that needs to be updated. wq, wv. There's no other weights that needs to be updated. And that there are like 3 layers: one for the encoder, one for the decoder, 2 for the decoders, right? So there are 3 layers. So our application goes like this. You open a trusty old Paint. So we have one layer. So one layer. This is for your encoder. Then we have one layer for a decoder, and then another layer for a decoder. There are 2 weights required. And then you have 3 inputs: 1, 2, 3. That gives the entire thing into a single output. And you have externally, because we are having cross attention, we have three inputs like this. I mean, my bad. We have 1, we have 2, externally we have 3, which gives you 3 weights. This also stores 3 weights, and finally gives you 1 weight. This is how the entire flow happens, like the entire, what's it called, encoder flow. Now in back propagation, what we need to do is, back propagation is we need to go in this direction. So first, what do you do? First, ReLU. So the feed forward part will now be, is there a feed backward algorithm? I don't think there's a feed backward. So backward is just going to be take the value and then you ReLU inverse, whatever ReLU inverse is. So basically what you do is to do a back propagation. Back propagation of DNA. First, unReLU, and then first calculate the loss. Calculate the loss. Then calculate L upon W Q M3. L upon WQ KM3 L upon W BM3. Then you have calculate. So that's like this layer. Where is our paper? Yup. Yeah. So we have done this part. Dude, I don't want to do backpropagation. It's so hard. What you're doing is unreload it. After unreload, you have to unmulti-head it, which is even more complex. Where is it? Wrap properly through the attention weights and dot product. Oh my god, that is so complex to understand. So what they're doing is entropy loss, and they find okay, they use normal gradient descent, but obviously Adams gradient descent, which is like optimized algorithm to optimize the weights. PyTorch Atom Optimizer. Wait, gradient descent is basically just theta 1 is equal to theta 1 minus alpha del L by del W1. That's it, right? So what we can do is we can use Adam, or we can use batch gradient descent or stochastic gradient descent. XG boost. Can we use XG boost? Because that's another fast one. What all functionalities do you have? SGD. Adam W. Adam X. SG. Okay, they all have only the basic. BFGS, yeah. Adam's algorithm is basically normal stochastic algorithm, but it has a few more add-ons at the end. So this is like the normal stochastic gradient. Normal gradient descent, but then at the end, it does a fancy concept. I don't know much about it. I only know about basic stochastic gradient and batch gradient. So code bias running. Do we actually want to implement Adam? Python Adam gradient descent. create like, okay, you create a matrix, so 4 inputs, 4 values for the matrix, and then you oh oh stamina, 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 stamina. Quite something, A. Quite something, A. Okay. So basically, using Atom Optimizer, you optimize the weights. Then the final weight you get, that's your data. What do we do? Go to code. That transformer. Inner transformer. And as Atom Optimizer. Inside we have a file which we'll call Atom py, which will have import numpy and p. Class Atom def parameters. Self that parameters with this. What the fuck is data? No. New weights. No. Oh. I comma b comma delta n minute self dot params and zip of self dot param comma gradient into self dot m of I is equal to self dot beta 1. This is the linear part plus self dot m of I plus 1 minus self dot beta 1 times grad. Is this in line with the algorithm? Yep. M of t okay. And then m hat is equal to m of I set beta 1 self dot t. What the fuck is a t? T is like the number of epoch or number of steps. Oh, okay, fine. And we had a self dot v of I one self dot beta 2 self dot t. Wait, is it actually par or is it just Adam optimizer? Mm. Mm. Yeah. P. Hmm. Encode line I. Oh, my bad. Hmm. Okay. Okay. That's it. Now let's try to understand what is Adam. Adam. Let's try to understand Adam, shall we? Let's go over here. Yeah. I don't know whether his will be copyrighted, but his is the best. Oh my god. No. No. Please, my friend Andrew, please don't copyright this. I just want to learn. This is strictly for learning purposes. This is not for entertainment. I do not promote anything from deep learning AI, and it's only for attaining knowledge of what Adam is. I'm not affiliated with deep learning AI in any shape or form. It is purely for my intellectual growth, and that's it. Please do not DMCA me.
During the history of deep learning, many researchers, including some very well-known researchers, sometimes propose optimization algorithms and show they work well in a few problems. But those optimization algorithms subsequently were shown not to really generalize that well to the wide range of neural networks you might want to train. So over time, I think the deep learning community actually developed some amount of skepticism about new optimization algorithms. And a lot of people felt that, gradient descent with momentum really works well. It was difficult to propose things that work much better. So RMSProp and the Adam optimization algorithm, which we'll talk about in this video, is one of those rare algorithms that has really stood up and has been shown to work well across a wide range of deep learning architectures. So this is one of the algorithms that I wouldn't hesitate to recommend you try because many people have tried it and seen it work well on many problems. And the Adam optimization algorithm is basically taking momentum and RMSProp and putting them together. So let's see how that works. To implement Adam, you would initialize VDW equals 0, SDW equals 0, and similarly VDB, SDB equals 0. And then on iteration T, you would compute derivatives, compute dw, db using current mini-batch.
Okay.
So usually you do this with mini-batch gradient descent. And then you do the momentum exponentially weighted average. So VDW equals beta, but now I'm going to call this beta 1 to distinguish it from the hyperparameter beta 2 we'll use for the RMS portion of this. So this is exactly what we had when we're implementing momentum, except that I've now called the hyperparameter beta 1 instead of beta. And similarly, you'd have VDB as follows. So 1 minus beta 1 times dB. And then you do the RMS prop like update as well. So now you have a different hyperparameter beta 2 plus 1 minus beta 2 dW squared. And again, the squaring there is element-wise squaring of your derivatives dW. And then SDB is equal to this plus 1 minus beta 2 times dB. So this is the momentum-like update with hyperparameter beta 1, and this is the RMS prop-like update with hyperparameter beta 2. In the typical implementation of Adam, you do implement bias correction. So you're going to have V corrected. Corrected means after bias correction. dW equals V dW divided by 1 minus beta 1 to the power of t, if you've done t iterations, and similarly V dB corrected equals V dB divided by 1 minus beta 1 to the power of t. And then similarly, you implement this bias correction on S as well. So that's S dW divided by 1 minus beta 2 to the t, and S dB corrected equals S dB divided by 1 minus beta 2 to the t. Finally, you perform the update. So W gets updated as W minus alpha times. So if we're just implementing momentum, you'd use V dW or maybe VDW corrected. But now we add in the RMS prop portion of this. So we're also going to divide by square root of SDW corrected plus epsilon. And similarly, B gets updated as a similar formula. VDB corrected divided by square root S corrected dB plus epsilon. And so this algorithm combines the effect of gradient descent with momentum together with gradient descent with RMS prop. And this is commonly used learning algorithm that's proven to be very effective for many different neural networks of a very wide variety of architectures. So this algorithm has a number of hyperparameters. The learning rate hyperparameter alpha is still important and usually needs to be tuned. So you just have to try a range of values and see what works. A common choice, really the default choice for beta 1 is 0.9. So this is the moving average, weighted average of dW, right? This is the momentum high range of values. Hyperparameters commonly.
Okay, so to understand this, thank you. Okay, so to understand what's happening over here is beta 1, these are like constants, these parameters that are like set, so we don't care about them. We care about what V and S are. So V is your moment and S is your RMS prop. So let's see what is a moment and an RMS prop. What is a moment and RMS prop? A moment in a context of optimization is a statistical measure for a distribution of gradients over time. Okay, so it's basically a smoother. So it's like trying to find the average, so like mean and then mean of means, if I'm correct. Mean vary. Okay, so a moment is basically a particular statistical algorithm that will smoothen your data such that all of them fall in a single line. So first we try with averages. So average is your first and most obvious way of checking the line over which the maximum number of points are covered. Second, you check variance. Variance is more stricter than mean. So you check with your variance if your data falls into that line. And in Adam, we have seen that we will use the first moment, which is your mean, and not the variance part. So in Adam, you're using mean. No, in Adam, you're using your first moment as well as your second moment. Okay. In Adam, we are calculating mean as your first moment, and instead of RMS, so what is RMS prop then? Okay, RMS means root mean square propagation. It is an adaptive optimization algorithm that adjusts learning rate for each parameter. I don't care about Geoffrey Hinton. This is basically variance, right? Yeah, this is basically just variance, and this is your parameter update. Okay, so basically what Adam does is that Adam's algorithm goes as such. Okay, so Adam algorithm is in each iteration find the first moment, which is your mean of the parameter, and you find the second moment, which is the variance of the parameter. Then we calculate the corrected, what is it called, the corrected first moment. Yeah, we corrected first moment, and we calculate the corrected second moment, and then finally the updated weights are then calculated using the loss, no, the cost, what's it, cost function derivative, which is corrected corrected first moment upon square root of corrected second moment plus epsilon. Corrected first moment divided by square root of corrected second moment plus epsilon. So this is basically Adam's algorithm. So any kind of deep learning algorithm that uses moments mean like average and variance, it's basically you will have to first find the average, then you find the mean of parameters, then you calculate their then in Adam you're calculating the corrected average of the first corrected average and the corrected variance. After you calculate the corrected average and the corrected variance, using that you form your derivative of cost function, and after using the derivative of cost function you can easily calculate your final optimal weights. Okay, that's nice to understand that. Yeah. What is T? Is T in Adam gradient? Times of iteration count. Yeah, So for each iteration, you're smoothing it even further. Yeah, okay, understand. Huh. Yep. Mm. This is calculating squared mean error. Hmm. Which kind of loss function did they use? They used an Adam optimizer with a 0.98. 4,000 steps. Oh my god. I'm not using regularization. Regularization, no way. No way, bro. No way. Let's open GitHub and add our code. Yep. And status. Did it break anywhere? Till now, nothing has broken. Let's go to GitHub. I could use Git, but I'm too lazy to use Git. Git is like too much brains remembering all the commands. Can't do it. So in back propagation, we really do that. That is Adam. Adam will come and fix our problems. Adam will solve everything. Adam will do it. Adam will solve all our problems. Adam. Wait, why are we running into 10 epochs then? Only one epoch should suffice, right? Why are we doing encoder decoder for 10 epochs? Are we dumb or something? Because you want to, training it 10,000. You only need to train it once. One flow. Optimization is done like X number of times, right? Or am I stupid? We do the flow once. Then we optimize the weights. And then we send it again. In our DNA is the attention process done once and the Adam optimization done X number of times, or is the attention also run for X number of times. Uh-huh. Humu. So, let's say our batch is initially 10. We're not like doing more than 10 right now. What we do is go to our main. We don't run this for 10 epochs. We run this for like once. We train once. In training, what we're doing is this is your forwarding. So we have a def forward eng embedded fr embedded, which takes in all of this.